Mute, so I'm not sure. Can you see this?
Yeah, I can see it, but that's always on.
Okay.
I think this is good.
There's a light that says mute and it's on.
It flashes when it's muted.
Okay, super. Alright. Hi everyone. Are you excited? I am excited. Alright, let's get started. My name is Sid, and I'll be talking about signature inference and property discovery. I've been working on this for about 4.5 months, so I will most likely forget to explain some stuff. If at any point anything is unclear, just tell me immediately, don't wait until the end, so maybe I can catch up. This presentation should take around an hour. I'll try to make sure to stay within the hour. I have a clock right here, but if I don't, also just shout and say you're too long or something. All right. So I have a long-term vision, and my long-term vision is that there is a future in which software actually works. Because I am apparently an annoying user because my software very often just doesn't work. Maybe I'm just actually a terrible user or not average or anything, but it just doesn't work most of the time. So I imagine a future in software works because it is cheaper to make software that works than software that doesn't work. Because one of the things I believe about software at the moment is that it is too often too easy to skip tests and get something that doesn't work but is good enough for now, and then we just get stuck with software that doesn't actually work. So the long-term goal that I have is that we never have to come up with tests manually anymore, because that is, according to me, the bottleneck in having to write tests. Now, the work that I'm going to be presenting is one step in that direction. We're not quite there yet, but I'm going to be presenting what we've done up until here. So back to the basics. Why have we made this thing? Well, apparently it is really hard to write correct software. Now, the first thing you might think to do is we make the machines write software. But then it turns out that making machines write software is actually really hard because you have to explain what it is you want them to do, and then it's also hard to describe to the machine what it is you want to do, and it turns out that describing to the machine what you want it to do is exactly what writing code is about. So, new idea. We'll write the code ourselves, but then we will make other code that proves that the first code is correct. Now, I'm not going to step on the toes of the people who work on formal methods here, but the point is that, well, first of all, you'll run into the trouble with Rice's theorem, but most importantly, you have to already know what it means for your code to be correct in order to be able to prove that your code is correct. So in practice, this isn't actually used most of the time. We'll have to resort to something cheaper. So, new idea. We'll write the code ourselves, and we'll write more code to test that our code was correct instead of proving it. Now, this is what's usually done in industry because it is cheap enough to do, but it's still not done enough in my opinion. So let's see one example here. This is a test well, this is actually just a Boolean, but this could be a test given that you have the right wrappers. Excuse the indentation, it's just that highlighting stuff, as I will do in a moment, doesn't happen on anything other than per line, so I have to. So the first problem we have with this kind of test, which we will call unit testing, is that you have to specify the input and output examples manually. And you have to say, this is the input, now you have to decide this is what my output should look like, make the specific case of the output example that you're looking for, and then assert that your function transforms that input in the output you want. So the first problem here is that you need to come up with the right examples, you need to come up with enough examples that cover all ways your code could go wrong. And we often miss a lot of cases. The entire point of figuring out that your code is incorrect is that you can't come up with the cases where it is not correct, right? So having to do that manually is a critical problem. And the second problem is that this is really expensive because you have to come up with these examples yourself. We usually don't do it. We don't come up with enough examples, or we don't come up with tests at all. So the way we fix the coverage problem is by using property tests. There we go. This is the property test. So here we say that instead of, for one specific example, my code works. Now we say that for all possible inputs, my code does something, and there is some property that holds about the output, right? So in this case, we say for all lists, if you sort a list, then it becomes sorted, right? Now, this fixes the coverage problem in a probabilistic way, because now your code works for random input, but it exacerbates the cost problem, because now you have to come up with generalized properties yourself. And for most programmers, this is actually even more difficult than writing unit tests, right? Now, there are probably people in the room here who would disagree, but believe me that there are people who find this more difficult, including me. So how do we fix this cost problem? Well, the idea is to discover what these properties are about our code automatically, so we don't have to come up with the properties that we will then want to test. So let's fix this cost problem, or let's try to fix this cost problem. There is an error in my slides. Okay, so we'll try to fix this thing. We'll try to fix that we have to come up with properties ourselves. This is actually wrong, but never mind that. So there is this something that does property discovery. It's called QuickSpec. And let's see what it does. Here's some code. You don't have to actually read all the code. The only thing you need to read is these lines. So there are two functions. One is called mySort, which will sort a list of orderable things. And there's a function called myIsSorted that will check if the list of orderable things is sorted. All right? And then QuickSpec will find that these functions are in scope. So there is true, the constant, and then there are a few other things. Now I say functions, but I also include constants. Let's not be pedantic about that. And then QuickSpec finds these laws. So it will tell you, we have this code, and we find these properties, and now this is almost testing code. You have to just add some arguments, and you make a lambda expression, and then you actually have quick check code already. So this could be included in your test suite as is. Now, the intention is not to automatically figure out what all the properties of your code are, so you don't have to think about it anymore. These are just suggestions. So you will be told, these are properties that may hold. Now, please check for me that these are actually properties you want to have hold about your code, and then you can add them to your test suite. All right? Now, before I go on, this is really cool. And I'm going to talk about some limitations, but that doesn't mean it's not really good work. There have been 2 papers about how to do this, and they're very well written, and the research is well done, but there are some limitations, right? First thing is, how do we use this, right? You have to write a bit of code, right? So this is the code you have to write, you compile it, you execute it, and then you get this output that you just saw, right? The problem is, you have to write code, and there are some more problems. You have to individually monomorphize all functions that are in your code, because you can only generate arbitrary input for monomorphic functions, right? If there are any type variables in your code, then you have to somehow make them non-type variables in order to generate the right input, okay? And then the second problem is you have to write code, and not just some code, you have to write a lot of code. In this case, you had to write double the number of lines of code that you're actually interested in. So there's 15 lines of subject code, the mySort, etc. And then there's 33 lines of QuickSpec code right here that you would have to write to find the properties. So this is not something you would just do in the middle of programming, right? This is quite a bit of effort, and this makes it completely impractical for my own purposes. And then the third problem is, this is rather slow. There are 2 papers about how you make this fast. So I'm going to describe to you what the dumb version is of this, of how you can find these properties. There are a lot more smarter ways to do this, but they're not asymptotically better. So it's actually still terrible. So what we do is we generate all possible terms of code, and then we generate the tuples of those, so we have equations. We make sure that the left-hand side and the right-hand sides have the same type, so that they type check, so that we can actually speak about the equation. And then we also check that the input to the 2 sides can be generated, with arbitrary in this case, and that the output can be checked for equality, so you can't really compare functions, for example. And then we run a quick check on all the properties that we find to see if the properties actually hold. All right? All right, so I've been working on a slightly better way to do this, and that's what I want to present for you today. We've been working on this tool called EasySpec, and this should solve most of the problems that QuickSpec has. And the first step in solving the problems is to automate the writing of all the code. Right? As you saw, this is the code we had to write. It turns out this is automatable. It's not trivial. I've been working on it for 4 months, but it's doable. Right? So the thing that QuickSpec needs is a signature, and here is the part of the code that defines a signature. And a signature contains the constants that are in scope, and this is actually a historical term. This should be functions. So these are all the functions in scope that QuickSpec will need to know about to discover anything. You also need to tell QuickSpec about all the instances that are in scope, because it can't just figure it out. So if anything that you define is orderable, you need to tell QuickSpec about the fact that this is orderable. And I'll show you how to do that. And then QuickSpec also does some optimization for itself to make things faster and to find the right properties. And you can help it with that by giving it properties that you already know to hold. All right? And then you can run QuickSpec with this bottom function here, and it outputs a signature. And the reason it outputs a signature is also for historical reasons. But what it does is it puts the properties that it found in this field background, so that you can use the signature that you get as the output for the next round if you ever want to run it again. Everything so clear up until here? All right. So the first step in automating this is automatically monomorphizing everything. So it turns out QuickSpec defines these types, capital A until capital E, that are actually new types over integers. And QuickSpec knows that these are supposed to be monomorphic. So all we need to do in that case is just make the type variables uppercase with some asterisks, but that's essentially what we have to do. And then the next step is, for any type class constraints, we also need to make this dictionary translation that GSG does internally, where anytime a type variable has a constraint, we have to explain in data what this constraint means. So in this case, we need to explain that capital A is orderable by giving a dictionary of the methods that are in orderable, or the functions that are in orderable, so that QuickSpec will know to give the function the right dictionary, so that you can actually order this big A, even if big A is not actually orderable. All right? Still with me? Right. So we automatically monomorphized these functions. Then we have to generate this expression that is the signature that we give to QuickSpec. So we have our regular function. We make this translation to a monomorphic function, and then we make this expression that defines a constant to put in the signature, where we just give it a name and then make sure that this dictionary thing is actually in the right order, I guess. So it turns out that you can ask GHC to translate a type class constraint into one of these dictionaries automatically, and that's with this mukdict function. Details really. And then we just make a signature expression with all of these constants that we've just found. All right. So the current state of what we've done then is as follows. We have some code here. This is supposed to have a really small scope. In fact, there are only 2 functions in scope. There is a reverse function and there is a sort function that do exactly what you think they do. And then we have the no implicit prelude extension just to make sure that there are only these 2 things in scope for now. And then we can run this command. It runs QuickSpec automatically, does all the magic that we just saw, and then we get some properties as the output. All right? So now you just press a button and you find the properties. All right, so now we've automated this entire thing, but the problem is that it's still very slow. As you can see here, this is a graph of the runtime of how long it took to run EasySpec with respect to the size of the scope, so the number of functions in scope. And this is a log plot, so the runtime you see on the y-axis is logarithmic. Well, it's on a logarithmic scale. And you see if you have 15 functions in your code base, it already takes more than 3 minutes. Right? So this isn't really useful for big code bases or for any code base at all. Okay. Now, the way we fix this runtime problem is quite complicated, so I will have to define some things. First thing we have to define is a property, and when I speak about property in this context, it's always an equation. And the equation is something like, if you reverse a list twice, then you get the original list, and this is actually short for the function that reverses a list twice equals the function that doesn't reverse a list. Okay? And in general, this is just an equation of two functions where on both sides the input and the output, the input is generatable by randomness, and the output is checkable for equality, and it doesn't diminish the generality to say that the inputs have to be equal. Still with me? Cool. So next thing I have to define is the size of a property. Can anyone take a guess what the size of this property is? It's 4. The reason it's 4 is because this is the maximum size of both terms. That's the practical definition. In general, it's quite a bit more complicated, and it's actually defined by implementation at the moment. The reason this is relevant is because we have to cap the size of the property at some point, because there could exist an infinite amount of properties about your code. So we have to just stop it somewhere, and we've stopped it at 7. In fact, if you have properties larger than 7, you probably don't want to put them in your test suite. Next thing we have to define is what a property of a function means, and it's rather simple. If a function occurs in a property, then this property is a property of this function.
Wait again.
If a function occurs in a property, then this property is a property of that function. So in this case, these two properties are properties of f because f occurs in them, and this last one is not a property of f because f doesn't occur in them, right? Then we define what a relevant function is, and we say that two functions are relevant if they both occur together in a property. So it's important to note that this only makes sense if you have a context where you have a set of properties and a set of functions. And in this set of functions, in this set of properties, we say that g and z are relevant to each other, but f is not relevant to h, because f and h never occur in a property together in this set of properties, right? So this only makes sense in the context of a set of properties, right? Still with me? Cool. So the scope is just all the functions you have in the scope in your code base. So everything you could use as a variable. Well, the GHC term variable, not the actual term variable. So everything that is in scope, everything is visible, everything that GHC wouldn't complain about not being in scope. Right? And then the size of your scope is the number of functions you have there. Again, I do include constants for practical reasons. And then the size of the signature that you give to QuickSpec is just the number of functions that you put in that signature. We're not going to speak about the size of the signature in terms of how many instances are in there, but that will be relevant in data research. Right, so now we have this automated but slow thing. And we actually set out to find 80% of the properties that you would find with QuickSpec in 20% of the time. That was the overall goal. Now it turns out this is nonsense because 20% of ridiculous is still not practical. In fact, this is slow for a number of reasons. First of all, the maximum size of the properties we discovered has to be bounded, because otherwise you could just go on forever. And the algorithm that QuickSpec uses is exponential in this maximum size. But if we bound it, that doesn't actually matter. The second problem is the size of the signature determines how long that QuickSpec run will take. Sort of. Well, most of the time there is an upper bound for how long it will take, depending on the size of the signature. Sometimes it's longer or shorter, depending on which properties you will find, which functions are available, how long it takes to run them. But most of the time, the problem is the size of the signature and not actually the runtime functions. Right? So this is where we had an idea. Instead of giving the entire scope to QuickSpec, we will just give a small part of the scope to QuickSpec, because we're actually not usually interested in the entire code base, but only in a small part of the code base, namely the part that you've recently been working on. So if you're coding along in your data, then you just write a new function, and the idea is that you then check which properties are there of this function, but you're not actually interested in all the rest of all of your code and the properties of how they relate, but only about how the code base relates to the function you just wrote. Right? So this is what we call the focus function. The function that you're interested in is the focus function, and in general we use a list of focus functions, so a smaller list of functions that you're interested in, a smaller list than the entire scope. Now the problem is, QuickSpec can only find properties about everything you give it to, everything you give to it. So if you don't include a function in the signature you give to QuickSpec, then it can't find any property relating that function. But so now we have to find interesting ways to give enough functions to QuickSpec that it does find interesting properties, but not too much so as to get the ridiculous runtime again. So we found that there is this way of decreasing the size of your signature in order to keep the runtime reasonable and still find enough properties. So the full background strategy is the top one here, is just the thing that QuickSpec does by default. So just look at all the functions in scope. And the empty background strategy is a strategy which ignores the scope and just gives the functions in focus to QuickSpec, right? Then you will find all the relevant functions, or sorry, you will only find relevant functions because everything relates to your focus, but you won't find much, right? So here's the runtime, and we see that this is fast enough for practical purposes. The problem is we don't find a lot of relevant equations, right? So as you would expect, we don't find a lot of relevant equations. So while this may be practical to run, you will only find equations like idempotency of your function. So if you sort a list twice, then it's the same as sorting it once. You will find those kind of properties, but only those, all right? Right. Next, we looked at other ways to reduce the scope and make a smaller signature. And here's one way to do this. We just thought about the stupidest things that could possibly work, and this is the first thing we could come up with. So we look at the Hamming distance between the names of functions, and we take the 5 functions in your scope that are the closest to your focus function and put them together in a signature. You laugh, but this is actually surprisingly good. So this is the runtime, constant time, as you would expect. So this is practical. The problem, sorry, this is not a problem. This is annoyingly good. It turns out we find most of the properties that we would find in the full background. When I say most, it's not actually true. We find almost as many, which is not the same as most, as it will turn out, but I'll explain that in a moment. So we find 8 on average instead of 10 on average, which is annoyingly good, because it turns out this is not as easy to beat as we would hope. So the next thing we did is, instead of looking at the names and looking at the Hamming distance between the names, we look at the Hamming distance between the implementations. So if you just look at which functions are used in the implementation of your function, and you make some sort of vector out of that in an infinitely dimensional vector space where a 1 means this function is used, a 2 means this function is used twice, etc. And you take the Hamming distance in that space, you just take the 5 closest ones to your focus function. Then this is still constant time, as you would expect, so it's still practical. And now we find a tiny bit more. So we find a little bit more relevant equations. All right, so another idea we had was look at the similarity of the type. So if you take all the subparts of a type, so just recurse through the type to find all the smaller parts of the type you can find, make the same sort of vector about this, take the Hamming distance, and find the 5 closest functions by type, similarity. Then this is constant time again, so this is practical. And we find a similar amount of relevant equations. And at this point, we thought, well, we can keep going on with these similarity measures. We find some other, we tried some other metrics. So we tried using an edit distance instead of a Hamming distance. We tried using the Jacquard distance instead of the Hamming distance. We also tried unioning the other strategies. And this all turned out to give something relatively close to what you just saw earlier. So we thought there had to be something better. And it's at that point we discovered there is something weird about this distribution. So this is a histogram of the number of different functions that are in any equation. And it turns out that between 60 and 70% of all the equations contain fewer than 3, so 2 or fewer different functions. And almost 90% of all the equations contain 3 or fewer different functions. So that means it does not make sense to give more than 4 functions to QuickSpec in a signature, because it will only find small-ish properties. But we can run QuickSpec more than once, right? So we can maybe run it more than once with very small signatures and still find a lot of equations. And that's the next idea. So then we define this signature inference strategy, which is where the name comes from of the talk, where we just give a list of signatures to QuickSpec and then combine all the equations in the end. But if we're going to give a list of signatures, we may as well give the output of what QuickSpec already found, the equations that we already found for optimization, back to QuickSpec. And that's why we tried it with a forest as well. So any child of a tree, the output of running QuickSpec on that signature could then be used in the background on the next run of QuickSpec. Right? But if we're using a forest, we might as well share the children, so we then made a directed acyclic graph of the signatures. So then we would run all of the signatures in topological order, reverse topological order, so that you can just share all the dependencies, make sure that QuickSpec knows about all the previous equations that we've already found, and then run QuickSpec a bunch of times so we still find a lot of equations and it doesn't take too long. And this is the next thing we came up with. We called it chunks. Historically it was called different, but now it's called chunks. And chunks does something really simple, where you just take first the focus functions, put them together in a signature. In this case that's just sort. So this node is a signature that only contains sort. And then we look at all the groups of true functions where one is in the focus and one is in the scope, but not in the focus. So all chunks. And put them in separate nodes that all point to this focus node. All right? So in this case, that means you put sort and reverse in a node together, and you put sort and ID in a node together, and they both point to the node that only contains the focus function. All still with me? Right. This runs in reasonable amounts of time. This is still linear time, so it's probably not practical for big code bases, but it may be a building block, so we tried it, definitely. And it turns out we actually find more equations than if you would use the entire signature, the entire scope in your signature. Now this may be weird because we thought we'd find something between 60 and 70% of all the equations. It turns out that the reason that we find more stuff is because full background, so what giving the entire scope, finds more stuff in general, but not necessarily more relevant things. So chunks finds a lot less equations, but it finds more relevant ones. And the reason is explained by this degenerative example. Is that the right word? Yeah. A degenerate example where you have a bunch of functions that are all increments of each other. Now if you run full background on this, then you find these equations. And the last one, so if you run full background with R being the focus function, then you find these equations, all of them, and only one of them is relevant to R. And it turns out that these equations capture the implementation of the functions exactly. And because all of the functions in this scope are available to QuickSpec, it only finds these most general equations, and only one of them will be relevant. But if you run chunks on it, then you don't have this entire context of the way they work together, and you find a lot of equations that are about R, but don't necessarily relate all the rest of the functions. So you find a lot more relevant stuff, but you find less stuff. And I argue actually that these may be better tests, because if you change one of these scope functions, then in the full background tests, a lot more of your tests would have to change. And if you use these tests, they're more encapsulating with respect to which functionality you're going to test. All right? Now, at that point, we thought, can we do any better, right? So we tried to come up with a way to conditionally run QuickSpec another time and maybe run it differently depending on how you found the output of the previous runs. And then we came up with this really complicated directed acyclic graph of functions that map lists, and it was annoying to implement and really not very enlightening. So then we thought there must be a more elegant way to do this. And it turns out there was. And you may not believe it, but this is actually more elegant. So what we've done here is defined generalized algebraic data type that just captures the syntax of a monadic expression that you would use to define a signature. So if you use pure, as in the applicative pure, then it would just construct one of these infer pure values. If you use fmap, then it would just construct one of these fmap values, etc. And then so this is just a monadic syntax tree, the first four of these. And then the last one is a special one where we define how to run QuickSpec, or how to make the runner of this thing run QuickSpec. So anytime you define I want to run QuickSpec, you get both the equations of the output and this thing called an opti token. And the opti token is just a way that you can say now in the subsequent runs, these other equations that we found previously will have to be put into QuickSpec to run the next one. Everyone still with me? Any questions here? Okay. So this is a much more powerful way to run QuickSpec without allowing I/O at all. So you can decide however you want to run QuickSpec in the subsequent runs without allowing for I/O and without restricting the person who is going to implement the signature inference strategy to any sort of directed acyclic graph, for example. And then we came up with this new strategy called chunks POS, which does exactly what chunks does. So you still have this star formation of chunks that all point to the focus node. But now also, for every 2 nodes that isn't the focus node, for every 2 of those that both find relevant equations, you will make a 3rd node that contains all 3 of those functions and run QuickSpec on those as well. So in this case, we will find that if you reverse a list before you sort it, then it's the same as just sorting it. And in this case, we find that if you sort the list, it's the same as sorting it after using the identity on the list. So in both cases, we find relevant equations. So that means we now make a new node with sort, reverse, and ID, and we may find even more things. That's the idea. Right? It turns out this is a lot slower. This is quadratic time in the worst case. But now we find almost double the number of relevant equations as we found with QuickSpec by default. So this is a great idea because it's still a lot faster than what you do if you just run QuickSpec by itself. So it's a lot faster and you find a lot more stuff. So this is, at the moment, the best strategy we have if you have time to wait. And the idea is to now use this in subsequent ideas we would have about signatures or about strategies to maybe first reduce the size of the signature and then run chunks POS. So if we can reduce the size of the signature to something that is either constant or logarithmic in size, and then run chunks POS, then we have something that is still practical to use on a real code base, but a lot, and also finds a lot more stuff, hopefully. We haven't tried this, we have some more time. So here's another overview of all the things we tried up until now. So you see that the 4th one here is the default, so this is what QuickSpec does. And then the bottom 2 are the best ones we have. The empty background is the first thing you saw, etc. And here's an overview of the runtimes. You see that everything we found in strategy-wise is more practical than the current default, and some of them find even more things. Right? So this is the current state of the art. We can run EasySpec on real code in a reasonable amount of time and find the properties of this code. And then we use these equations that are found. We check if this may be something that we want to have hold about our code. We put them in our test suite, and we didn't have to consider what we had wanted to test at all. So in this case, I would want to put the last 2 equations in my test suite, certainly. And if I wanted to put the second one in my test suite, I would want to add a comment, and I probably don't want to add the first one. But you can still choose yourself because this doesn't force you to use any tests. So this looks really cool in my opinion. The problem is, this is research. And it turns out that making research tools has the disadvantage that we have to publish and we don't have time to make this work on real code. So this only works for functions that are in scope for which the type is also in scope. And the problem is, for example, error in the prelude has this type class constraint called with stack trace, and with stack trace is not in the prelude, so you can't run EasySpec on anything that imports the prelude. This is fixable, we just haven't done it yet. This code also just crashes on partial functions, as you may expect. This is also fixable, but we haven't done it yet. This only works for built-in instances. So QuickSpec knows about some instances. For example, it knows that integers can be generated and that integers are orderable, but it doesn't know about everything in the prelude, and it certainly doesn't know about anything that you've defined locally. The data has to have an arbitrary instance, and the arbitrary instance also has to be in scope, which is usually a problem because you put your arbitrary instances in your test suite and not in your code. This also doesn't work well with the C preprocessor because we use Haskell source extensions, which doesn't like it. And at the moment, it doesn't work for higher kind of type variables. So if you use any monadically parametric code, then this won't work because we have to be able to monomorphize it, and higher kind of type variables are not necessarily easy to monomorphize. These are all technical problems. This is all fixable. I just haven't had the time to do it. All right. So now I'm looking into getting funding to make this work on a practical scale in industry for real code, as opposed to on my examples in my research. There is also still research to do, so we want to maybe go faster. We want to make sure that this is still practical on real code, so you can do it in a few seconds instead of hours. Or maybe we want another UI where you run the property discovery overnight for the newest piece of code that you wrote, and then in the morning you make your test suite. Maybe, we don't know yet. We also only look at functions in scope, so we didn't make up new functions, which you may want to do. For example, if integers are relevant to your code, then you may want to include 0 as a constant. Or if lists are relevant, you probably want to include the empty list as a constant, so that these are definitely included in the properties that you find. We also want to have a look at whether this works for effectual code. At the moment it doesn't, but you can imagine that any effectual code can be modeled as non-effectual pure code, given your input and output types are large enough to maybe include the universe or something. So in theory it works, but in practice we haven't tried it. We've also been assuming that all equations are equal in importance, which is most likely not the case. We just haven't found a meaningful way to distinguish or to order equations in terms of relevance or how important they may be in your tests. You still have to decide that manually. So these are all things that we could research still, but at the moment I'm really more interested in how we may be able to apply this in industry and how we can find the manpower to make this work. So here are some proof of concepts. So you have QuickCheck, QuickSpec, these are the links. QuickSpec is very much a proof of concept. I would actually argue that QuickCheck is also a proof of concept, but they're maybe offending people, so never mind. EasySpec is definitely a proof of concept. You probably don't want to run this on your own code, but you can try if you want to work on it. Right, so this is the entire information part of the talk. I haven't talked about who I am, and I'm only going to do it now so that I didn't cloud your judgment beforehand. I studied here. This is my master's thesis, so that's why I've been working on it for 4 months. I wrote some Haskell in open source, a lot of Haskell in open source. I taught Haskell at the university here as well in the second year. And I'm looking for a job. So if anyone thinks I want to hire this guy, come talk to me afterwards. Here are some links as well. That's it for now. It turns out I'm a lot faster than I thought I would be. But if there are any questions, feel free to go ahead. Yes.
Can you go back to the problem slides, like with the practical problems? Yes, this one.
Oh.
Yeah. So just to understand with what the current limitations are, so when you say the problem with error, for example, when exactly does it arise? Is the problem already there if I just use it somewhere in my function, or if the error actually pops up? Or can you not like construct like theorems that somehow contain error in them?
So the problem will only manifest itself if your signature inference strategy selects error in the signature, because if you then give it in the interactive evaluator to GHCI, it will say, I don't know about this type.
All right.
Because you saw I have to manually annotate all the expressions with the type that they have, and if the types are not in scope, then it will complain. So it will just not work then. And in the case of full background, that means if anywhere in your scope, you use error, then this will already not work. More importantly, also, if you use error, even if this would be in scope, it's still partial, so it will still crash, right? So that's the current limitation with that. Anyone else? Yes?
More of a practical question. So basically, when the process when you would be coding would be you run the property discovery, you see these are my properties for the code.
Yeah.
These are all the ones I want in, and then you convert this into a unit test that can be run automatically.
Yeah, exactly.
Okay.
And the way you make this into unit tests, so let's have a look at properties here. The way you make these into tests is you add lambda xs to the front, and then this is a property test. So that's all you need to do to make this into test code.
Yeah.
So that's not the thing we focused on,
Yeah.
but it's doable. All right.
And another question, which is an understanding question actually, one thing I didn't quite follow was how the other strategies that were not the full one can generate more outputs essentially. Is there something in the full one that doesn't actually consider all the possibilities? I first understood it as it just like checks everything it can up to a certain size, but after that it just seems like the restrictions that you make should only generate subsets of that. So where did I miss a part?
Oh, okay. So can you imagine if you have the reverse function, then if you reverse a list twice, you have the original list.
Yeah.
But if you reverse a list 4 times, you also have the original list.
Mm-hmm.
And if you reverse the list any even number of times, you have the original list. But the full background thing, or any of this properties discovery, will only find the first one, because as soon as you find reverse, it will have already found this equation, and then will just substitute as an optimization reverse by identity. So it will only find the most general properties. It's not actually true. If it finds a more specific property afterwards, then it won't include it anymore in the output. And that's actually why this is why you find more things in chunks, because you find the most general properties if you use full background, but that means there are fewer properties. For example, you don't find this here, QQ of PR. You don't find that because we actually can define P as IQ. So this is maybe not a good example. The thing is, this is actually a more specific version of one of these.
So
we
basically the full background like short circuits, right? And you stop like recursing, and
Yeah.
with the F1 you can.
Yeah, exactly. So that's why we found more stuff in chunks, and I actually think they're more reasonable to put in your test suite, but that may be an opinion. Yes?
Does your code first need to be correct before you can find good properties for it?
Yeah, so everyone asked me that. The point is that this code will not know what correct means until you start testing it. And the point is that you don't know, you haven't tested it yet, right? So this will only find properties that hold about the code as is. Whether you think your code is correct or not, it doesn't know about that. So it will only find the properties of the code that is there. It won't find properties of the code that should be there, right? So in a sense, it doesn't. So yes, your code has to be correct in order to find the correct properties.
But you then hope that if you see properties, you might see, hey, this can't be right.
Exactly.
And so, okay.
Yeah.
That's your debugging process then.
Yep. So one of the things I expected to find was if you make a character uppercase, then it becomes uppercase. This turns out not to be true, because 0, for example, is lowercase and there is no uppercase version. So if you uppercase it, it's still 0. So it is not true that if you uppercase a character, then it becomes uppercase. And so that's exactly one of the things we found. I saw another hand. Yes.
So 2 questions. First one, which data set did you use to generate all the assumptions which you got and the test items? And the second question is, actually it's not a question, just did you thought about making sure that you don't create fragile tests? Because it's very simple to make, to get 100% code coverage, but it's super fragile tests, which will always cause you to, which will always make you to change the tests if you change some line of your actual code.
Yeah. So as for the data set, I made up a bunch of examples that don't crash given these limitations. These.